Good morning, everyone. Welcome to day 4 of the Encontro Nacional da ENSPM. I'm Diogo Arsenio. We're getting together such a fine conference, especially given the challenges of the virtual setting. I think this has been great. I've enjoyed very much this conference so far. I hope you too. Should I work? It's not working.
Good morning to everyone. So Diogo is here. He is the chairman, but she has some problems with internet connection. So perhaps at a certain moment at the end, he can say some words. We can start with Isabelle Gallagher from the École Normale Supérieure de Paris. She will present a very nice and challenged theory about the derivation of the Boltzmann equation from a particle systems theory. This is a very old problem and many mathematics is here. We can now listen. Isabelle, please. Thank you, Diogo.
So thanks very much. Can you hear me? Yeah. So sorry, I don't know what's something happened maybe to my internet connection. I'm not sure exactly. So please tell me if there's a problem with the internet connection at some point. Can you hear me? Yes, no problem. Okay, perfect. So, well, thank you very much for inviting me and for the introduction. I'm really very happy to be giving this talk this morning. So I guess you can see my slides as well. Perfect. Okay, so I'll be talking about a joint project I've been having for many years now with, yeah. Yeah, is that okay? Okay, now can you hear me well? Perfect. So yeah, this is a project I've been working on for a long time with Thierry Bodineau, who's in the École Polytechnique, Laure Saint-Raymond and Sergio Simonella, who are both in the École Normale in Lyon, so all in France. And so the general question is trying to understand if you can derive fluid mechanics or dynamics equations from particle systems. So that's the general subject we're trying to work on. And so today I've tried to show you some progress that has been made in the past years on this question. So it's a subject that's sometimes a little bit technical. So I'll try not to be too technical, but if you feel it's getting out of hand, just please ask questions on the chat or yeah, don't hesitate to stop me if it gets just too much. Okay, so let me just start with a general question. So as I said, the question is, in some sense, you're looking at a fluid and there are essentially maybe two ways of describing the movement of a fluid. You can either discuss each of the particles of the system and try to write down equations on each particle. So they're all made of atoms, right, or molecules, and you can write down equations of movements for those atoms. And this is one way of describing the fluid. And the other way would be to write down the fluid mechanics equation, like the Navier-Stokes equation, the Euler equation, right? And obviously, those systems are very different, but they're supposed to describe the same object. But one thing you could maybe discuss is it interesting to write down the equations on each particle, or us at our macroscopic level, or do we rather want to understand the macroscopic equations like the Navier-Stokes? So both make sense, but the equations we're interested in are rather the, let's say, macroscopic equations like Navier-Stokes. So the question Hilbert was asking was, is there a way mathematically to explain how to go from one description to the other by some kind of limiting process? Okay, so that's what I'll try to discuss today. So as I said, to start with, you could write down equations for each of the particles if you like. And so here, of course, everything here is in an ideal setting. We're trying to do this from a mathematical point of view. So I'll decide that all my molecules or atoms are identical hard spheres. Okay, so of course it's not very physical, but at least we can try to write down something. Okay, so for today, the microscopic model is I'm giving I'm given a large number of hard spheres. Okay, I give them labels I, J. So I and J are labels between 1 and the number of particles in my system. And they're just satisfying Newton's laws, the easiest possible equations you can write. So the velocity here is the time derivative of the position, and the xi's here will be, let me write that here. Let's say they're sitting in a periodic box. Okay, let's make things simple. And the xi's are the centers of my hard spheres. Okay, so I'm just modeling my equations, just writing down the equations for the centers of my balls or spheres. And so VI is the velocity. So here VI will be in the whole space, RD. And what's happening is that I'm going to assume here that there's no forcing on my system. So the acceleration is 0. Okay, and each particle has identical mass, which I'll be taking equal to 1. To make things, again, as simple as possible. Okay, so that's just the equations for my hard sphere system. My particles are just going in straight lines. And of course, that happens very well as long as they don't meet. But of course, there are a lot of particles, and the probability that they will cross each other and it will bump one into the other is very, very high. Okay, and so you have to decide what happens when two particles meet, and that's written here. And you have an equation actually relating the outgoing velocities, VI, Vj, which are here, to the incoming velocities, V prime I, V prime J, which are here. Okay, those relations you don't have to remember at all, of course, but it's just a usual Huygens or Descartes or Snell-Descartes laws. Okay, it's an elastic collision, so the momentum is conserved, the energy is conserved, and just to understand what this epsilon here is, the epsilon is just the size of my spheres. Okay, so the diameter of my spheres is epsilon. I have an epsilon squared here because I'm normalizing the vector linking both centers of spheres. Okay, so xi minus xj is just the vector linking those two hard spheres, and I normalize them by epsilon, since epsilon is the diameter of the spheres. Okay, so those equations are just the usual equations you'd expect when you have an elastic collision. And so you see here, I'm writing a large number of equations because if I'm in dimension 3, for instance, then I have 3 components for x, right, for the center of my spheres, and I have 3 components for v, and then I have n particles, so I have 6n equations to write. And of course, n is huge here. It's something like 10 to the 23, right? So I have a huge number of equations. They're coupled by those collisions. And so this is probably quite hard to study. And anyway, as I said at the beginning of this talk, it's maybe not so interesting to understand where each particle is at each amount of time, right? I mean, for instance, if you're just sitting in a room like you probably are today, and if you open a window, then you're going to have some air coming into the room. And you could be interested in knowing if the temperature of the room is going to get higher or lower, for instance, okay, depending where you are. But it's not if you knowing what the velocity of each particle of the air coming into your room, knowing this velocity is not telling you exactly what the velocity of the fluids that's coming towards you is, or what the temperature is. It's related, obviously, but it's not exactly the same. Okay, so understanding the temperature or the velocity of whatever flux of air is coming towards you is related to the velocity of each individual particle, but it's very different. Right. Another example: if you're in a room and you're not moving, then it looks like the air is standstill, right? It's not moving. But of course, each particle of the fluid is moving. Okay, so it's really very different to understand gas at equilibrium and the movement of each particle, because each particle is moving, whereas the gas is at equilibrium. So there is a difference we need to understand between the movement of each particle and whatever we're experiencing at our level. And one way of understanding that was suggested by Boltzmann. So actually Hilbert in his question had said that you could use Boltzmann's equation as a model, as some kind of intermediate step between the particle system and the fluid mechanics equations. So I'm writing here Boltzmann's equation, which is written in terms of a function f, the unknown function f here, depends on time, so whatever time I'm computing this function. It depends on x. X here is, you could imagine, just like one particle, okay? So it's telling you how many particles at time t are exactly at this position x, or roughly at this position x, with velocity v. Okay, so this is the distribution function. There are much less variables here. I only have t, x, and v. Okay, so if d is equal to 3, I have 7 variables, right? And it's a function of 7 variables. And it satisfies this transport equation. So I guess a lot of you have never seen this equation before. So I'll try to explain what this equation means, okay? So for the moment, let's just focus on the left-hand side of the equation. So you have here a transport equation, right? It's telling me that this distribution of particles which at time t are at x with velocity v is exactly the same thing as the distribution of particles which were at time 0 at position x minus vt and velocity v. Okay, that's because on the one hand, I'm saying here that all my particles are going in straight lines. So if there were no collisions on the right-hand side, I'd have 0. Okay, and I'd be done. Now, the thing is, we've seen in the previous slides that my particles do collide. And by the way, I only mentioned binary collisions. I only said 2 particles meet. I never said what happens when 3, 4, 5 particles meet. That's because you can prove rather easily that in some sense, the set of initial data such that collisions happen with more than 2 particles, that set of initial data is of measure 0. So I'll just forget in all my talk here the possibility that 3 or more particles might meet at some given time. I only look at binary collisions. So that's why my right-hand side here is a bilinear term, a function q of f and f. And let's look at how it's defined. So this looks horrible, but we'll try to understand slowly each term defining q of f. So again, it's a binary term, and it's telling you, it's a right-hand side, right? So it's telling you how you can feed f, meaning how you could have more particles at time t with position x and velocity v, or in the contrary, you could have less. So maybe let's look at how you can lose particles of velocity v. Well, what can happen, and that's its minus sign here, because I didn't tell you, but f is a probability distribution, so it's non-negative in particular, and it's also of integral 1 for each time. So f is non-negative. So if I have a minus sign here, it means I'm losing something, okay? And what we're saying here is that you could choose any velocity, okay? So I'm integrating over velocities. So it's just like a Lebesgue measure, right? So I'm taking any velocity, v1, and what can happen is that a particle with velocity v1 hits my particle with velocity v. And when I do that, then I'm losing a particle of velocity v, because after collisions, the velocities have changed. Okay? So if a particle of velocity v hits a particle of velocity v1, I produce a particle with another velocity. So that's a minus sign here. Okay? So f1 here means f of v1. On the other hand, what could happen is that a particle of velocity v prime hits a particle of velocity v prime 1, just like we saw in the drawing before. And that way I'm creating a particle of velocity v, okay, with the relations, what we call scattering relations we saw before. Okay, so if that happens, then I have f of v prime times f of v prime 1, and this is creating an f of v. Okay, so this explains, in some sense, the right-hand side. I'm integrating also against all omegas. Omega here is just like x1 minus x2 divided by epsilon, right? That's a unit vector we saw in the first slide. Just telling you, you could have any kind of angle between the relative velocities and the relative positions of my spheres, and that's given by omega. Omega here is an angle, so I'm integrating actually here over rd times s, d minus 1. Okay. So the last term I haven't discussed here in this integral is this collision cross-section. That's the word we use to define this term. This term is the scalar product between the relative relative velocities and the vector relating the centers of each sphere when I had my hard sphere system. You see that if this term here, if it's 0, that means that my particles have relative velocities which are orthogonal to their centers. Right? Then the scalar product is 0, and that means actually I'm not doing anything. I have a grazing collision. I'm not creating or removing a particle. Everything is constant. Okay, that's why I have a 0 here. This doesn't appear. Now, the worst that can happen in some sense is when particles have a head-on collision. That means v minus v1 is parallel to the centers of my particles, and this is the largest possible number you can have here. Okay, so this cross-section is telling you in some sense the strength of your collision. Okay, so I haven't proved anything here. I'm just defining and explaining each term of an equation, which is known as the Boltzmann equation. Now, one of the things we have to do here today is to understand why this equation has anything to do with my original particle system. Okay, question one. And question two will be to see why this equation has anything to do with fluid mechanics. Okay, and Hilbert is telling you, and we'll try to see why, that this equation is, again, in some sense, an intermediate step between particles on the one hand and fluids on the other. Okay, I forgot to tell you one thing, is this alpha here. This alpha is a number, okay, a positive number, and it's telling you in some sense, and we'll try to see later on why and how, the strength of collisions. Okay, so when alpha is going to infinity, that means I have many collisions in my system. If alpha is 0, there's no collision. And finding fluid mechanics actually will be letting this alpha here go to infinity. Okay, a lot of collisions. Alpha is actually the inverse of the mean free path. Okay, so alpha will be going to infinity. That means you have a lot of collisions, and then fluid mechanics will come out at some point. So maybe before I go into more details about the relation between particles and fluids, let's just study a tiny bit the Boltzmann equation. So here it is again. And so if you're a PD person, and if someone gives you an equation which is supposed to come from physics, the first thing you want to do maybe is solve the equation, meaning prove there is a solution to this equation, given some initial data. But to solve the equation, you have to see in what kind of function space you should solve it. So what are good quantities that would be, for instance, conserved by the equation? What are norms on F, which a priori, then you have to prove things, would be conserved from, by the equation? And the traditional way to do this is to say, well, let me take a test function phi, so very, very smooth function, and maybe let's just suppose for the moment it depends only on v. Okay, and then I want to see in what way this function, which might be still a function of, which is still a function of t and x, in what way this could be conserved. Okay, this, you see, if you integrate against all velocities, this becomes macroscopic in some sense. You don't care about velocities of particles anymore. So it makes sense to integrate against all velocities if you want to get a fluid mechanics equation. You want to know all possible velocities, what they produce in terms of the density of particles in x. And that will actually give you a fluid mechanics equation. So it does make sense to look at such a thing. And I want to know how this evolves in time. So I just want to take a time derivative of that. Okay, which, if everything is as smooth as you want, just means understanding in particular what happens to Q of FF times phi dV. If this is 0, for instance, for some phi, for any f, that means that the quantity I've written here will be conserved. Because the right-hand side will be 0, well, actually it will be transported. Okay, so let's see, if for what functions phi do I have Q of FF phi equal to 0? Now, you probably don't remember what Q of FF is, but if I tell you that if I integrate Q of FF against V, then everything becomes symmetric in terms of V and V1. Maybe you can believe me on that. Then computing Q of FF times phi is the same as 1/2 Q of FF phi of V plus phi of V1, because V and V1 are symmetric. Another thing you can do, another game you can play, is change VV1, sorry, for V prime V'1. If you do that and you change omega into minus omega, you haven't done anything. Okay, because of the change of variables I'd given before. If you change VV primes and at the same time, sorry, there's a typo here I haven't seen. This is a V1. At the same time, you change omega into minus omega, you haven't done anything. So in the end, what you have is 1/4, because you've done 3 more changes of variables, of phi plus phi1, that's because V and V1 are symmetric, minus phi prime plus phi prime. Okay, so that's just an equality. If everything is smooth, of course, I'm just pretending I can do what I'm doing. Okay, if everything is smooth enough, then this is an equality. And if I want this to be 0 for any function f, that means I need this thing to be 0. Okay, and now it's a theorem that, and I won't prove it, at least it's easy to prove if phi is easy enough to prove if phi is smooth. It's much harder if phi is not smooth. Anyway, you can believe me that the only way to have this 0 is the following. Either phi is a constant, obviously 1 + 1 - 1 - 1 is 0. Or phi is equal to v, or any linear combination of v. Why? Because I have a conservation of momentum bind a collision, which says that v plus v1 minus v prime minus v prime 1 is 0. Okay, and I also have conservation of energy, which says that v squared plus v1 squared is equal to v prime squared plus v prime 1 squared. So actually, if phi is 1 or v squared, then obviously this is 0 because of my particle system. But then the theorem says it's equivalent, actually. It's the only way to have this to be 0. Okay, so what I'm saying here is that the Boltzmann equation remembers that my original particle system had conservation of mass, constant, momentum, and energy. Okay. Now, what else can you discover from this equation? So it's slightly more difficult, but not really, that to notice that if you replace in my previous computation phi by log of f, if you're allowed to do that, okay, so f is non-negative, assume it's positive, and assume you're allowed to do whatever you want, then because of the convexity of the function x log x, in some sense, then this q of ff log f will always be non-negative. Okay, so with the minus sign, it's always positive. Sorry, with the minus sign, it's always non-negative, sorry. Okay, that's just because if you replace here by a log, you have log of f, f1 divided by f prime. Okay, so this d of f here is always non-negative. And so that's known as Boltzmann's H theorem, which is telling you that f log f is decreasing in time. And this is known as the entropy. Well, the mathematical entropy, the physical one is the opposite, okay? So the entropy is decreasing in time. That's one quantity you know will never blow up in finite time, okay? Because it's always controlled by the initial data. Now, the last thing you can ask is what will be stationary solutions to your equation? That's also an interesting question. So obviously 0 is a stationary solution, okay? Is there any other? Well, the thing that's necessary is to have a stationary solution, you need this thing to be 0, q of ff log f. Why? Because if it's not 0, then it's going to decay in time and the solution can't be stationary, okay? Now for this to be 0, that means log f has to be like my function phi before, which means a constant or b or v squared. Now you remember f is in L1, so f can't be an exponential of plus v squared, it has to be an exponential of minus v squared. Okay, so here are the some equilibria. Then you could also have an x dependence I won't be talking about today. You could have a local equilibrium. Here I want a global one, so I'm only taking functions depending only on v. And so equilibria of my Boltzmann equation, meaning a stationary solution, are those Gaussians or Maxwellians. Okay, so maybe we can also remember that. So if I take something which is uniform in x, okay, density equal to 1 everywhere in x, and Gaussian in velocities, this actually cancels every term of the equation separately. dt, dx, and the right-hand side. Okay, so now we know a few things in the Boltzmann equation. We have some conserved quantities, we have a decaying quantity, and we have a global equilibria. This actually, this H theorem I mentioned before, was sort of an issue when Boltzmann discovered that. So I just want to say that in passing, but I think it's important in some sense to notice that because this entropy is decaying in time formally, then the Boltzmann equation is time irreversible. Okay, because if you reverse time, the entropy will be increasing in time. Okay, and you're not allowed to do that if you're reversible. But now if you go back to my original hard sphere system, that's reversible in time. Why? Because if you just change the arrow of time and all velocities, the sign of all velocities, nothing has changed, right? Or if you take a movie of a perfect billiards, and you pass the movie the other way around in time, nothing will be shocking to you. Okay, so the original dynamical system is time reversible, but this limits, whatever that means, we haven't seen why it's a limit. This is time irreversible. And that at the time raised a lot of confusion, and people were arguing quite strongly about this issue. The other issue is that when you have dynamical system, you know that solutions satisfy a recurrence theorem. Okay, and that seems to be contradictory with the fact that it's not hard to prove, at least formally, that solutions of the Boltzmann equation will converge to the Maxwellian in large times. Okay, that's a general principle in some sense that you expect. If you have some kind of equilibrium, if you have some kind of large time dynamics, it should be something which is stationary, and the stationary solutions are the Maxwellians. So on the one hand, you have a relaxation to something. On the other hand, you have recurrence. That seems to be also a paradox. So, okay, it's actually not hard to lift this paradox. We might talk about that later on. The reversibility paradox is a little bit maybe more subtle, but we'll be mentioning that later on as well. Okay, so as I said at the beginning, the Boltzmann equation is in some sense an intermediate step between particles and fluids. So in this talk, we won't be talking about the way you go from Boltzmann's equations to fluid mechanics. Okay, you can ask Diogo all about that. He can tell you a lot about that and other people. But that's not at all the aim of this talk. But it is known, and this is a very general and blunt statement, and of course you have to put assumptions, but it is known that, for instance, the incompressible Navier-Stokes equation is a limit of the Boltzmann equation. If you let alpha go to infinity, if you wait a long time, that means you should wait for a time alpha t. Okay, and alpha is going to infinity, so that's a kind of diffusive regime. And if you start taking averages, as I told you, you should average against velocities. Actually, what you should do is average against the constant, against v squared. That will give you a kind of macroscopic density, momentum, velocity, and energy. Okay, and those three quantities will satisfy a fluid mechanics equation. If you just let alpha go to infinity, I'll give you maybe more statements later on, you'll get an Euler equation. If you let time go to infinity as well, then you'll get a Navier-Stokes equation. So there's been a lot of work on this subject. We can maybe discuss that later on in the questions and answers. But for the moment, I won't tell you more or hardly anything more about that. So let me just give you a few pictures to tell you what's known. Okay. So what I want to do now is take limits. So on what can I take limits? Well, what I can do is take a limit on the number of particles. Okay, obviously a gas is made of a huge number of particles, and actually the Navier-Stokes or whatever fluid mechanics equations you'll find are obtained by letting the number of particles go to infinity. At the same time, I'm in a periodic box, I should let their size go to zero, which is also reasonable, I guess, from a physical point of view. Okay, so the number of particles is going to infinity, their size is going to zero, and now I need to scale all that. And the scaling I'll do is to assume that my gas is rarefied, meaning the volume it's occupying is very, very small. Okay, and that's really an important scaling I have to make. I'm only studying here perfect gases, actually. Okay, so n epsilon d, the volume occupied by my particles, is extremely small and going to zero when n is going to infinity. So that's in some sense a kind of a perfect situation. Now I'll do something else. I want to count, in some sense, the number of collisions I have in a given time. So I give myself one particle here, okay? And I want to know how many particles this particle is going to hit in a given time. Well, all I have to do actually is compute the size of the tube this particle is going to follow in time t with velocity v. And the size of the tube is just, in some sense, if t and v are essentially 1, the size of the tube is epsilon d minus 1. Okay, so the diameter of my particle is epsilon, up to some constants. And so if I have only one collision on average in time 1, that means that n, which is the number of particles, times epsilon d minus 1 should be equal to 1. Okay, and if this guy, n epsilon d minus 1, looks like alpha, that means I have alpha collisions in time 1. Okay, and that's the scaling we'll be using all the time. N epsilon d minus 1 is given. That's known as the Boltzmann grad scaling. And so let me just give you in a few slides some well-known results going from particles to fluids and the scalings people use. So if you want to forget about Boltzmann and just go directly from particles to fluids, at least as far as I know, the only way you can do that is putting some noise in the original dynamical system. For instance, you're going to assume that when particles collide, they don't have this collision, elastic collision I was mentioning before, but what will happen is that the velocities will be changed in some random way, for instance. Okay, and then you let the amplitude of this randomness go to zero, and you do get all kinds of fluid mechanics equations like compressible Euler, like the heat equation, like compressible Navier-Stokes. Okay, there are a lot of models that can be derived directly from the dynamics, molecular dynamics to fluids. So you can do that in a number of settings if the original system, the dynamical system here, has some noise. So it's not deterministic. What we are interested in this project is having a deterministic system originally, and then getting fluid mechanics. So again, we're going to use Boltzmann's equation. So the scaling we're going to assume for the moment is, as I said, n epsilon d minus 1 is given by number alpha. Okay. Now, what's known, and I'll try to discuss that afterwards, is that there is a limit we'll be discussing from the particle system to the Boltzmann equation on a short time interval, and the size of the time interval is 1 over alpha. Okay, that's Lanford's theorem, which I'll be discussing. And okay, the only way, at least well-known ways of getting better than this 1 over alpha used to be, that's two references I give here. In the case of a Lorentz gas or a tagged particles, that means you have one particle you're specifying and you want to know what it's doing, and the other particles are at equilibrium or are actually just potentials, not moving. Okay, in that case, you can actually get a Lanford's theorem for a large time, and okay, I'll be talking a tiny bit about that later on. But in general, if you just have a general situation, the time on which you can prove convergence to the Boltzmann equation is 1 over alpha. Okay, and the problem is, remember, if you want to get fluids, as I told you before, you need to let alpha go to infinity. And so again, there are theorems, as I said, going from Boltzmann to fluids. Okay, they're known, but since you need alpha to go to infinity, then Lanford's theorem breaks down. Okay, because his theorem is only known on a time 1 over alpha. So that's the reason why, for the moment, we can't go from particles to fluids, because the scaling you need to get to fluids is impossible. You can't make it compatible with Lanford's theorem, which validates the Boltzmann equation. Okay, so what we want to do, the program would be to do the two arrows at the same time, let n go to infinity under the scaling, get Boltzmann, and then let alpha go to infinity and get fluids. So this program has been achieved in the past in two easy, in some sense, situations, which are linear situations. So as I told you, the tagged particle, you just say one special particle changes velocity, for instance, or changes position, and all the others are at equilibrium, and then start studying the movement of that tagged particle. In that case, you can produce a linear Boltzmann equation in the Boltzmann grand limit, and then it's very easy to see that the linear Boltzmann equation converges to the heat equation. And you can't do both limits at the same time, because this equation is linear, you can actually have everything uniform, and even having alpha going to infinity is possible. So you can improve very much Lanford's theorem in this situation and go all the way, well, do the program you wanted, but in a very easy situation of the heat equation. Okay, so easy in the sense it's the easiest equation you can think of, I guess, if you think of fluids, just the heat equation. A little bit more complicated, and I won't be talking about that more today, is finding nicer fluid mechanics equations, still linear, which are known as the Stokes-Fourier equations, which are a linearized version of the Navier-Stokes equation. So that was also possible. It was a little bit more technical, but you can still do the whole program in this situation. Again, it's a linear situation. It's not exactly a linear Boltzmann equation. It's a linearized Boltzmann equation. It's well known that it converges to the Stokes-Fourier limit. The only hard part was proving the Lanford's theorem in this situation, but that was possible. Okay, but today I want to study a nonlinear situation. So I don't want to study at all one tagged particle. I want to get the Boltzmann equation. Okay, and actually, so our program these days is to say it's probably too hard to get the Boltzmann equation for a long time. It's for the moment when we don't know how to do it. So what we want to do is understand first, of course, Lanford's proof, and study fluctuations around his proof, trying to understand what's going on when Boltzmann's Lanford's theorem is not working in some sense. Okay, and the more we understand what's around Lanford's theorem, maybe we'll get to improve his proof and maybe one day get a global result for the Boltzmann equation. Okay, so we're not going to improve Lanford's theorem today at all, but we want to go around it, trying to understand fluctuations and large deviations around the Boltzmann equation. Okay, so that's the goal. And again, the idea is to say if we understand that as much as possible, then maybe we'll understand also the original limits better. Okay, so that's the idea. So maybe now for the rest of this talk, things are getting a little bit more technical, but I hope it will be still understandable. And so let me explain the setting. Okay, maybe I'll just go to the Lanford's theorem, but I want to explain how we do that. So start again with my original dynamical system. Let's say I have n particles. I'm going to to say where they are by calling xi, again, the centers of my particles. But now I want to look at the distribution function. So it's a function of x and v, of all x's, of all v's. Okay, I'll call z the collection of all x and v's. And all I know is that my distribution function of n particles is sitting in a phase space where I need the positions to be larger than epsilon. So the diameter of my particles is epsilon. So my phase space is a set of all positions and velocities such that the distance between two x's is larger than epsilon. Okay, so that's the phase space in which I'm writing my equations. Now, what I can give myself is my initial data for my particle system. Okay, so what I'm going to assume here are two things. First, I'm going to assume that all my particles are identically distributed. Okay, so they all satisfy at time zero this distribution f0. Okay, which is a nice continuous function, maybe with Gaussian bounds. Okay, so this product here means that all my particles are identically distributed in my phase space initially. Okay. Now I know my particles are sitting in this phase space. Okay, so I have to put this characteristic function. And now the last thing I'm going to assume here is that the number of particles n is not fixed, it's not given, right? Which is what we call the grand canonical formulation. There's no reason why you should know exactly how many particles are in the room in which you're sitting. Okay. What you can just say is that it's given, for instance, that's the setting of the grand canonical formulation, is given by a Poisson distribution. So mu epsilon here is the average number of particles. That's exactly a Poisson distribution. Okay. And the average number of particles should be given by this Boltzmann grad scaling. So 1 over epsilon d minus 1. Remember, Boltzmann grad was n epsilon d minus 1 equals 1. Alpha is 1 here. So the average number of particles is 1 over epsilon d minus 1. Okay, and you can check that with this definition of my initial distribution, then the average number of particles, if n here is the number of particles, this average number of particles is exactly mu epsilon. Okay, so then of course you normalize everything with this partition function, which just guarantees that this guy here is of average 1. When I say an average, I mean I'm taking a sum over n and I'm integrating over all x's and all v's. Okay, so when I'll talk about an average, I'll be always saying that I'm summing over n and I'm integrating in the phase space against this distribution here. Okay, so there is some kind of probability theory behind this. Okay, there's no statistics. My initial system is deterministic, but what I don't know is the number of particles and the distribution. So I'm going to integrate against f0. Okay, and I'm going to sum over the number of particles. Is that okay for everyone? Okay, so now the question is, how does this evolve in time? Well, the answer is perfectly simple. My particles are going in straight lines, so this is a simple transport equation. Okay, there's no choice about that. The only thing that can happen is that two particles collide, meaning in this formalism, that means that at some point, I'm going to have boundary conditions on the boundary of this guy here. Okay, the boundary of this guy is xi minus xj equals epsilon. Okay, so if my function w at some point is sitting on the boundary, then I have to change its velocities. If the velocities are coming out, I have to replace them by the incoming velocities. That's the boundary condition. Okay, so I have a simple transport equation with a rather maybe complicated boundary condition. Okay, this is probably the worst slide of this talk. It's just a definition, so we just have to accept that in some sense. But what I'm interested in, or what Boltzmann is interested in, is, maybe we should look at this last line first, is the one particle correlation function. Okay, what's the distribution of one particle? How do I compute that? Well, I'm going to take the average of the empirical distribution. I'm going to take a test function h, compute it at each possible position. Okay, n is the number of particles, also a random variable, and then I take the expectation of that, divide by the number of particles. Okay, this by definition is the one particle correlation function. Okay, so you have to accept this definition, and if you take that as a definition, you can compute one way of computing this f in terms of the initial data w. So here I've given you the n particle correlation function. You can do the same for n particles. I take a function of n variables. I want to know where they're sitting. So I'm going to average against all possible labels of particles, okay, and numbers of particles. And this gives me the n particle distribution function. And in terms of my original distribution, what I'm doing here is summing over all kinds of correlations between n equals 0, n plus 1, n plus 2, blah, blah, blah. I integrate against all that for all possible p's. Okay? And this is equivalent. So you can define this and you get this integral and you can just compute that. It's not hard. So maybe for the moment, all you can remember from this is that I'm given an initial distribution. And from that, which I gave you before, from that I can compute the one particle correlation function or any number of particle correlation functions. And Boltzmann's theorem is going to explain where this guy is going as time evolves. Okay, here's Lanford's theorem. Lanford's theorem is telling you if you look at the one particle correlation function, it converges towards the solution to the Boltzmann equation. Okay, that's exactly what we wanted. We have the Boltzmann equation. Now we know what to do. We have to let epsilon go to infinity. That means the average number of particles going to epsilon go to 0, sorry. The average number of particles is going to infinity. Then this function, when I look at what the equation it satisfies as time evolves, okay, this is the initial data. Now I can look at what happens as time goes on. At the limit epsilon goes to 0, I find the Boltzmann equation. Okay. And he proves more than that, actually. He tells you also that the n particle correlation function converges to n copies of the Boltzmann equation, which means that as epsilon goes to 0, my particles become independent. They will all have the same distribution function, which is the solution to the Boltzmann equation. And that's the theorem, okay? So that was what Boltzmann expected. That's what Lanford proved. And that is true only, again, on a small time interval, 1 or 1 over alpha if you've given yourself an alpha. So maybe all I'll tell you now is how do you prove this theorem? So it's a huge proof. It's very complicated, but the idea is not so hard. If you want to do it formally, it's just a few lines. If you want to prove it, it's harder. So what you can do is just look at this n particle correlation function at time t. That's the definition. I know the equation this guy satisfies. It's a simple transport equation. So I just plug in the transport equation into this integral and see what happens. And what you get is a transport equation for the n particle correlation function. Okay, that's because this guy had a transport equation. Except at some point you have to commute this domain, the characteristic function of a domain with a space derivative. Okay, and if you do that, then you have some kind of a green formula coming out, which is telling you sometimes you're hitting the boundary. You have to be careful. When do you hit the boundary? Well, when one particle amongst the n is hitting a new particle, let's say I call it n plus 1. Okay, so this is a little bit tricky, but if you just plug in the equation and integrate, you get exactly this. You have to choose what particle is hitting another one in my n plus 1 to n plus b. Since everything is symmetric, let me call it n plus 1, and you get exactly this equation. Okay, so the right-hand side is a collision term, and you see what's hard here is that it involves one more particle. I used to have n particles, but since these n particles could hit a new one, only one new one because I only have binary collisions, on the right-hand side, I have f epsilon n plus 1. Okay, and then when epsilon goes to 0, this guy is going to look, if you take n equal to 1, for instance, you let epsilon goes to 0, this guy is f epsilon 2, which will look in the end like 2 copies of f. Okay, this you have to prove, which is roughly f epsilon 1, 2 copies of. But this has to be proved, of course. Okay, but if you do that, if you replace f epsilon 2 by 2 copies of f, you get exactly the Boltzmann equation. Okay, if you look at this even from far, this looks roughly like the Boltzmann equation. Okay, so maybe I'll just explain a little bit in a less sketchy way the way Lanford does this. What he says is the following: you can translate the equation we wrote in an integral form. This is the free flow of n particles, and then, well, not the free flow, but the flow with the collisions, and then I just do a duhamel formulation of the right-hand side. Okay, so it's equivalent, if everything is smooth enough, to the original equation I had here. Okay, just put the flow and write down an integral formulation. And then his idea is to say, since I have an f epsilon n plus 1 here, I can do the same game. I can replace it by free flow of n plus 1 particles plus a duhamel term. Okay, and then I'll have a f epsilon n plus 2, and I can play the same game. So in the end, you have a whole series of terms, And the interest of this formula is that you've expressed the solution in terms of the initial data. Okay? Because every time I see something depending on t, I replace it by the flow applied to initial data plus something else, and then I do it again and again and again. Okay, so what you can read on this formula is that to compute the solution, the n particle correlation function at time t, what you should do is flow your n particles for a time t1, collide with an n+1 particle, with a n+1th particle, flow those n+1 particles, collide with a new one, flow, blah, blah, until you've ended the story. And you do that for any m, it's a series over n. Okay. Now, the only way of getting this to be a proof now is, one, to prove that the series is converging, which is not so obvious, and two, proving there is a limit to each of the terms of the series. Okay, if you've done that, then you've found a limit, and you just have to recognize the Boltzmann equation in that limit. Okay, so since I only have a few minutes left, I'll just tell you, I'll just skip this till I get to the end. There we are. So how do you prove the convergence of the series? Well, each of these collision terms counts for an n because you had a sum from 1 to n. Okay, so since I have all of those, in the end, I have some kind of a factorial m. Okay, and it's fixed here. But this factorial m is compensated exactly by the simplex in time on which I'm integrating. Okay, so in the end, that's why you have a short time. The bound, the way that you're proving the series is converging, is just because you have a CT to the n. Okay, you're just putting absolute values everywhere and just counting terms, and that's why you have a short time. Convergence of the series, well, it's not hard to converge in this guy here. You just say that when you had your interactions with an epsilon, just change them into a pointwise interaction. That's done. That's easy. When you have your flow here, that's the hardest part of the proof in some sense. You want to change this flow where you have lots of particles colliding into a flow where particles do not recollide. Meaning, if two particles meet at some time, if you want to find the Boltzmann equation, you need to remember that all particles become independent. That means that if two particles collide, they can't have collided before. Right? If not, they're not independent. They can't even have collided with a particle that collided with a particle that collided with a particle that collided with them before. Okay, so their collision trees have to be different. If not, they're not independent, and Boltzmann just doesn't work. Okay, so that's probably the hardest part of the proof, is proving that when two particles collide, when epsilon goes to 0, then they haven't met before, or anyone that met each other before either. Okay, and once you've done that, you know your initial data looks like a tensor product of initial data, and you're done. Okay, just check that the Boltzmann equation satisfies the same kind of series, and then if there's only one solution possible, then you're done. Okay, just one comment before I move to fluctuations, and then I'll be done. Why did irreversibility happen here? Well, the irreversibility happens because of recollisions, right? You're eliminating recollisions. But a recollision is exactly saying I have an arrow of time. Because if two particles recollide, okay, if you put the time in the other way, it's a collision. They haven't seen each other before. They just recollided. If you change the arrow of time, it's a collision. So the definition of saying I'm recolliding is saying I have an arrow of time. Okay, and there's a way of writing down Lanfear's theorem, which really very precisely shows that even the statement of the theorem is irreversible. And again, why did I have a short time? Just because when I wanted to control my series, which is in some sense controlling how large my collision trees are, I put absolute values somewhere, and I had a CT to the m, and that's why I had a short time. Okay, and even if my initial data was at equilibrium, actually everything should be a constant. I'm not able to see that in the series actually. So even for initial data at equilibrium, I have the same short time restriction actually. Okay, which is very bad, but as often in nonlinear equations, it's very hard to use the structure of the equation to get global solutions, right? So here we just don't use the structure and we lose everything. So let me just finish. Okay, I'll just skip that. Sorry, this is bad. Okay, I'll just finish by fluctuations. So Lanfear's theorem, one way of understanding it is a law of large numbers. So this is an exercise, this line here. It's not hard to check that the way I stated Lanfear's theorem, you can prove very easily the following statement. The probability for the empirical distribution to be far from its average, the average is Boltzmann, Okay, that goes to 0 when epsilon goes to 0. That's really a reformulation of the Lanford's theorem. Now, the question we try to address is, now can we look at fluctuations? Fluctuations, usually you multiply by the square root of the number of particles. Okay, so here I'm multiplying by the square root of the average number of particles. This is a fluctuation field. Okay, it's still a kind of probability distribution in some sense. And now my question is, how does that evolve in time? So at time 0, this is not 0, right? Because I have fluctuations due to the number of particles in particular. At time 0, this is not 0. This is given by a Gaussian white noise, and you can compute easily its variance. So I know exactly what this is at time 0. My particles are all identically distributed, and it's just an easy computation to see this as a Gaussian white noise. Okay, and I can compute its variance. So now the question is, what happens as time evolves? And here's a theorem, and I'll stop here. The theorem is in some sense, well, maybe it looks surprising at first, but actually it's not, maybe. So the theorem is telling you the following thing. I look at this fluctuation field at time t. What happens as time evolves? Well, you first have something you could expect maybe, which is a linear equation. This fluctuation field is going to be pushed by the linearized Boltzmann equation around the solution f. So I have this solution f, and the fluctuation field is just a fluctuation, so you expect it to satisfy something which is linear, and the only thing you can linearize around is the Boltzmann equation. Okay, so it's rather natural to expect that this fluctuation field will satisfy some kind of a linearized Boltzmann type equation. Okay, but what happens is that you have a noise which appears. Okay, initially you just had this fluctuation field, which you know exactly, but as time evolves, a noise appears. This noise actually was conjectured by Spohn in the 80s. It was proved at equilibrium in a number of papers. But what happens is that even out of equilibrium, you have the same kind of noise. And this noise, and I'll stop here, comes from recollisions. As soon as two particles recollide, this guy is not 0 because you have particle at place x1 hitting a particle at x2. Okay, it's exactly this right-hand side. And recollisions, one recollision is creating a noise which appears at the order of fluctuations. Okay, so okay, I'll stop here. So we were sort of happy about this result because it was something that was expected. You can actually prove the same thing in large times at equilibrium. That's something that's in progress, and you can work much harder and obtain actually all orders of fluctuations and a large deviation theorem. But I won't tell you more about that right now. I think I've run out of time. So thank you very much for your attention.
Thank you, Isabelle. I don't know if everyone can. I apologize for the introduction. My connection dropped. I hope now everything goes well. You'll believe me that I had a lot of nice things to say about Isabelle, but I will be for another time. So I'll start with the question, and my question is the following. So there was a lot of talk about dispersion maybe helping in the process of deriving the Boltzmann equation. Of course, I think you mentioned everything on the torus, but if you think you are on the whole Euclidean space, as if you wait long enough, particles will always be moving away from each other. And in that sense, dispersion should maybe help. Do you see anything? Is there any clue, any hint that it might help extend the existence time and the convergence?
Yeah, that's a very natural question. I don't know. So the simple answer is I don't know. The only thing that worries me in some sense is that if you wait really much too long, then you'll just have free flow, right? If particles have all dispersed. So you have to find some balance between the two. So yeah, I think dispersion should help probably to reduce the number of collisions, I guess. And so maybe we could do better on some scale of time in the whole space. But for the moment, we're really worried about collisions taking time on a short time interval already, recollisions, and so. I don't see, well, for the moment, of course, it's a very natural question, but I don't see how that can help. For the moment, we haven't been able to use that at all. For the moment, we treat recollisions. It's a little bit more difficult in the torus because particles come back all the time. So you have to deal with that. But if not, apart from that, we deal with recollisions in the same way, unfortunately, in the whole space as in the torus. And so, yeah, I don't know how we could use dispersion, unfortunately.
Yeah. Okay, great, thank you. And I was under the impression that Lanford claimed also some results close to vacuum. Is it the same proof, or?
I'm not sure. Maybe it was more Chershniani, Ilner-Pomerenti, maybe also Lanford. I'm sorry, I don't remember exactly. But yeah, you also have results. So I should have said that near vacuum, you can prove actually a quasi-global convergence to Lanford's to Boltzmann's equation. That's right. So near zero, right? That's true. And as far as I remember, the arguments are not exactly the same, but I'm not so familiar with that, so I wouldn't guarantee that. But in fact, yeah. Well, if F0 is very small, the time is better. That's for sure. Okay, you actually have a lower bound on time, so you can plug in a very, very small F0 and improve Lanford's results. That's for sure. But I don't think that's the way they did it actually. But I'm not so sure.
Okay, thank you. We have here another question. Isabelle, could you please explain if there is any mathematical reason for considering hard spheres and not other type of interactions like Maxwell molecules?
Right, good question. So, okay, I won't answer for Maxwell molecules right now. What you can do is put a potential. If it's compactly supported, everything is fine. Just the proof is more technical, but in the end, it's exactly the same thing. You just change a little bit the collision cross-section, but everything works fine. That was done by King, actually, a student of Lanford, and then we sort of revisited that with Laure and Benjamin Texier. If you put other interactions, to my knowledge, essentially nothing is known. I know a student of Sergio Simonella is looking at boundary conditions with Maxwell boundary conditions. And it's very hard and hardly anything can be done. If you put compactly supported, non-compactly supported potentials, then the only thing that's known, I think, is a student by Laure, Nathalie Haï, former student by Laure, who proved a result when the potential is not compactly supported, but decaying like 3 exponentials, I think, in X, which is very, very hard already. I mean, 3 exponentials, it looks almost compactly supported, but technically it's really hard. And yeah, I guess understanding your question is very, very natural and very good. I don't know what's known. I think nothing is known. I guess one of the problems, as usual, is understanding recollisions and also, well, grazing collisions. And there are a lot of new problems that will appear if you study other kinds of interactions. But yeah, definitely this should be done. Hard spheres looks worse in some sense because the dynamical system is not so good. But it's much easier from a technical point of view, just to understand recollisions, for instance.
Okay, great. Thank you very much. I think now is a good time to stop. So I'm going to thank you again for an amazing talk. And so that's the end of this first talk for day 4. And I'm going to remind everyone that everyone's welcome to explore the parallel sessions by clicking on the other stages. The parallel sessions are starting now at 11. So thank you again, Isabelle, and everyone have a great day.
Thank you very much.
Thank you both.
Thank you.
Thank you.